Hello, can everyone hear me? Okay, so I already got a really nice introduction from Anton. So yeah, I'm Tony, I'm representing Dedaub, we're a security company. And yeah, the title of today's presentation is how to predict the impact of EVM upgrades. So what we're going to be covering today is two studies that we did for the Ethereum Foundation last May. The first study is about self-destruct removal. So that's EIP 4758 and EIP 6780. So they're two kind of competing proposals for how self-destruct was going to be removed. I'll give you kind of like a quick rundown of what self-destruct is and what it does, or now what it did. We'll then understand why it kind of needed to go. We'll understand how it was being used. And then I'll give you kind of the verdict for that initial study. The second kind of thing that I'll get into is the transaction and receipt route serialization changes. So that's kind of related to how now we have a difference between consensus layer and execution layer. Consensus layer uses this new SSZ format. Execution layer uses an older serialization format known as RLP, recursive length prefix. And so there's some changes there with how MPT routes are constructed. So yeah, we'll get into like what exactly is changing. You'll get a little bit more of an understanding there, why it needed to change. We'll also then cover how we found contracts which were doing RLP decoding, because that's kind of like crucial to understand what the impact would be. We'll find RLP blobs in call data, and I'll give you the verdict for the second study. So as I mentioned, the first study, it's EIP 4758 and 6780, or basically in short, removing self-destruct from the EVM. So a TLDR of self-destruct, basically self-destruct, it clears up a contract. So it resets the nonce, it clears the storage, it clears the code, and you can also send all of the ETH in the address to an address of your choosing. There were also at one point like gas refunds associated with self-destruct, and kind of the purpose of introducing self-destruct was to kind of promote state cleanup inside of the EVM. So I don't know if anyone here like runs a full node, but they're kind of expensive to run. So if we can get people to clean up things when they no longer need them, then we could hopefully have reduced the impact of like running a full node. And we saw like other things. For example, you had storage slot gas refunds, which were also kind of to promote state cleanup. If you didn't need a storage slot and you reset it to 0, you would have got a refund. This kind of mechanism did actually sadly end up getting abused through gas token. I don't know, does anyone here remember gas token? Yeah, so the point of gas token was basically you could create a storage slot, you could fill in a storage slot, or you could create a contract when gas was low, and then when gas was high, you would destroy the smart contract or reset the storage slot, and you would get the gas back, and you kind of like offset higher gas costs. So that was one abuse we saw over the years. It wasn't really the reason it needed to be removed, because that got mitigated in EIP 3529, which basically slashed these refunds. Another kind of abuse we see with self-destruct is mutable code, otherwise referred to as metamorphic smart contracts. So there's kind of various ways they're done. It's kind of a combination of create to and self-destruct. I'll get into that a little bit more later. There was a proposal that came up whilst we were doing this study, 6913, which is sec code, which kind of aims to like make this a part of the EVM. But I won't really get into that. I just thought I'd mention it since it did come up whilst we were doing the study. So to kind of break down EIP 4758 and 6780, I'll summarize 4758 as deactivating self-destruct. So what I mean by deactivating self-destruct is we're going to rename the opcode from self-destruct to send all. We're not going to touch the code, we're not going to touch the state, we're not going to touch the nonce. And the actual reason we wanted to go about this change is because of a movement called the Verge. So I don't know if you keep up with the roadmap that Vitalik publishes, but there's numerous kind of like phases going on in parallel in Ethereum. One of them is called the Verge. The Verge is related to originally Verkle trees, but now just verification in general. The Verkle tree component is basically you take a Merkle tree and you replace its like hash proofs with what's called vector commitments. And the really nice property you get there is that you can do proofs over these Verkle trees with reduced data sizes and smaller proofs. Because basically, if you look at the tree there, you can actually prove a path through the tree without needing to send these sibling data. So you're able to actually kind of do these like parent-child proofs, and then you can like combine them and compress them into really condensed proofs. The problem that self-destruct causes with this is you can kind of have an unbounded number of state updates. So think about it, over numerous transactions, you could fill up lots and lots and lots and lots of storage slots. You self-destruct, all of those storage slots get cleared, they get set to 0. You have a really large payload update. And the reason the payload update is like a problem, at least the size of it, is because in the future we want to have these stateless light clients. So basically the light client wouldn't store any state, they would need to have all the states sent to them, and these large, unbounded, unpredictable state updates would cause a problem for implementing this, as well as, like implementation complexity in the nodes for like kind of keeping the state around for a number of, blocks or epochs. And that's kind of why we wanted to remove it. So 6780, I can kind of summarize as restricting self-destruct. And basically, it's the exact same proposal, except for the fact that if you self-destruct within a single transaction, it acts as it originally did. And the reason that this is okay is because you still have bounded state updates, and you're not really like committing to the actual state root. The reason this was proposed is because some people were kind of using this pattern. It doesn't have the same negative consequences, and we needed to evaluate like if this was actually better than 4758. So the way we went about doing this study, there's this like really nice tracing interface that's provided by Geth, or we use Aragon internally because it's like a bit more performant. But basically, you can hook into the EVM during its execution. The things that we care about here are capture start and capture end, as well as capture enter and capture exit. These basically are what's triggered whenever you have a call frame. There used to be capture self-destruct. I don't remember if that was an Aragon specific thing, but now self-destructs are actually kind of like modeled using call frames, which is kind of interesting since they don't actually initiate call frames, so they're like pseudo call frames in terms of tracing during the execution. And I'll like touch on that a little bit more later. So yeah, we recorded all contract creations and self-destructs. We specifically looked at ranges 50 million to 17.23 million for our study, since that was like the most recent data. We cared about what people were actually like actively doing. And we saw like 9.5 million creations split into 1 million crates, 8.5 million crate 2s, as well as like 420,000 self-destructs. So the first thing that we saw was metamorphic smart contracts, so mutable code on chain. So most people are kind of under the assumption that smart contract code is immutable, and it's kind of not. So yeah, the reason that this works is because using create2 or even create, you're able to kind of manipulate. I'll show you the patterns a little bit later, but to give you kind of some numbers about this, during like, I think we saw 170,000-ish redeploys. We saw one contract, if you look at the table on the left for you guys, we saw one contract that was redeployed to the same address 848 times. We saw one contract that was redeployed with 33 different bytecodes. And the main kind of use case we saw for this was MEV bots. So if you have an MEV bot on chain, you've built up lots of balances, allowances, permits, etc. on chain. It's very kind of expensive to transition all of that state to a new address. Maybe some of it you can't transition. So if you can upgrade your MEV bot in place because you've made it more efficient, you've had a new strategy, it makes your life like a lot easier. So here's a couple of the ways people are able to do metamorphic contracts. The first pattern is like what's called create3. Essentially what you do is you have a deployer contract that has constant code. Because it has constant code, you can always deploy it to the same address. So you create to it to an address. You then call a function inside this contract deploy, which basically is just a light wrapper around create. It then creates your metamorphic contract. And the key here is that create depends on the message sender and the nonce. And since we can reset the nonce using self-destruct, what we could do is we can self-destruct the deployer. We can redeploy it in place because it was deployed using create2. and then we can create with an arbitrary payload to the same address, and that's how we have our metamorphic contract. The other pattern is what's known as the metamorphic factory pattern. And basically the way that works, you have a factory contract on chain, you send it the code that you want to deploy, it deploys your contract to kind of like an arbitrary address, it then deploys your metamorphic contract with a constant init code, so you're using create2, and all the init code of the metamorphic contract does is it just takes the address or wherever it was deployed, does a code copy, and sets that as the return data. And then it sets its code as whatever you wanted it to be. And to kind of reiterate, because it has constant init code and it's created with create2, you can self-destruct it and recreate it in place. The other thing we saw is pseudo call frame. So it's kind of like a interesting behavior of self-destruct, but self-destruct doesn't actually initiate a call frame, which allows you to circumvent fallback functions. So whenever you execute a self-destruct, what it does internally in the node is just takes the address, it subtracts your balance and adds your balance onto the address that you're sending it to. And it doesn't actually initiate a call frame. So usually when you send ETH, you have to actually like send some amount of gas with that, since code can actually execute when you're sending ETH. You can have some like quirky behavior with this. So if we look at the WETH contract, you can see the fallback function is payable, and it calls deposit. You should kind of know what deposit does. It just increments your WETH balance and emits a deposit event. If you look at the total supply function for WETH, the total supply function relies on querying the ETH balance of the contract. So it doesn't actually do any accounting in the deposit or the withdraw functions. The reason this is like problematic is because basically you can increase the ETH balance of the WETH contract without actually increasing the amount of WETH that's distributed to users. And you do this by sending ETH to WETH using self-destruct. And if you actually sum up all the kind of WETH allocations, and you actually take a look at the ETH balance of WETH, it's off by about like 1,925 ETH. It doesn't really pose any issues to users because you can still like liquidate your ETH. You can convert your WETH. You can convert your WETH into ETH and ETH into WETH. It's just kind of like an interesting side effect of the fact that it doesn't initiate a call frame. We also saw people using self-destruct just to do arbitrary transfers. So if you look at the line of this transaction trace, specifically like the one originating from the arrow, you can see that someone creates a smart contract, they pass some value, 0.0125 whatever ETH, and then that contract just instantly self-destructs and sends all of its value to the specified address. And if I take the init code and pass it through the decompiler that we developed at Dedaub, it's like one of our fundamental technologies. The decompilation is on the bottom right. All it does is it takes the address from the end of its own initialization code and just sets that as the address for the self-destruct. And for example, this was being used by 3F Mutual to send funds. So to kind of break down everything that we saw whilst we were doing this study, we saw about 10 protocols that were deemed affected by EIP 4758, of which about 3 were considered high impact. But then if you look at EIP 6780, we didn't really deem any protocols to be affected by this. Both the proposals fix the metamorphic contract issue that I mentioned earlier. And EIP 6780 was actually included in the Denkun hard fork that you probably heard about from other speakers today. So that happened last week. Nothing's collapsed, so everything went well, I hope. Getting into the second study, it's migrating the root serialization from RLP to SSZ. So basically, you might have heard of this like thing of ETH2, essentially. We have a separate consensus layer and a separate execution layer. ETH2 uses this new like serialization format known as simple serialize, SSZ, over the original serialization format that we used, RLP, recursive length prefix. So SSZ has numerous advantages over RLP. The ones we care about the most are that it's Merkle first and that it's indexable. And the reason that like this property matters is because of this thing that I mentioned about the verge, where we want to increase like the provability powers for like clients and stuff like that. So the two EIPs are EIP 6404, which basically transitions the transactions route from being a Merkle-Patricia tree constructed using RLP encoding into a SSZ route. And this is being done on execution layer because the transactions route on consensus layer was already an SSZ route. As for the receipts route, it's also migrating from Merkle-Patricia tree to SSZ. And this is being done for both execution and for consensus. So the important kind of thing we need to understand in terms of who's going to be affected by this change is that we're looking for people who are using transactions routes and people who are using receipts routes. And the way that we figure this out is that they need to be in some way manipulating RLP data inside of their contract to be performing proofs over these routes. So we need to look for RLP like decoding or encoding. So let's kind of understand what RLP is. So there's 5 kind of cases for RLP. You've got single byte, string of bytes, long string, a list of items, and a long list of items. And they're kind of specified by prefix ranges. So depending on what your prefix range is, there's a way to get the actual data out and figure out the length of the data. I can actually show you what this looks like in pseudocode. And you can see the function like decode RLP. We've got a nice if-else chain. And so this is actually the pattern that we want to detect on chain. How would you go about finding smart contracts that look kind of like this or have a function that looks like this? And the important thing to note is these constants. So we have these constants that are actually used in comparison operations. And so we want to look for contracts that have these constants. And the reason that you have to have these contracts constants with RLP data is because RLP data is dynamically sized, it's non-indexable. Remember I mentioned indexability as an advantage to SSZ. You have to have these constants to do RLP decoding. So if you look at the top left, I have a disassembled view of bytecode. And you can see that they are pushing one of the RLP constants, 0xC0, to the stack. And then a few kind of operations later, we're seeing a comparison operation, and then we're seeing a jump. So if you just naively look over like the bytecode and you look for contracts that have the necessary RLP constants, you get about 25,000 bytecode results. So that maps to even more contracts. It's pretty infeasible to go through 25,000 in a 2-week study. So we needed to be a bit more clever. Now, you could say, well, really, we care about these RLP constants being used in comparison operations. And we can see that there is a comparison operation, 2 operations later. But the problem with doing it on the bytecode itself is that you can have numerous stack manipulation operations or random operations in between the less than operation or the greater than operation being used. So really what we need to do is we need to lift this. I already kind of mentioned we have a decompiler, and that's actually what we see in the middle kind of like code block. So that's the decompiled version of this. And if you see the line of code that originates from the arrow, we can just see less than variable RLP constant, so the 0xC0. And so we can see straight away that, okay, it is actually being used in a comparison operation. So we index all the code on chain, we've decompiled it all, we have it all in our database, and we can run this really nice like SQL query over it, where basically we just look for a variable being assigned to the result of one variable being compared with an RLP constant. The actual query is like a horrible regex that you can look at the end of the slides. I'll link it. But you need to account for example, plus and minus 1 to account for the difference between greater than or equal to, and whoops, go back there. And yeah, so when you run that query over the data, you go from 26,000 to 556. So it's an order of magnitude less. It's actually kind of doable within 2 weeks. We wanted to take it a step further and be a little bit more precise, and we ran something known as a data flow analysis. And so what the data flow analysis does is basically we see, if you look here, the less than operation flows into the green variable. The result of the green variable flows through an is0 operation into the purple variable. And then the purple variable is used as the conditional operation of your jump I. And what this means is that the result of the comparison operation is actually dictating the control flow of the program. And that's what an if statement is. An if statement has a Boolean operation which determines the control flow of the rest of the program. And when you run a data flow analysis and you combine it with transaction data, you get down to a result set of about under 100 contracts, which is very feasible to actually go through manually in like 2 weeks. So some of our team got started on the manual investigation, and the rest of our team, we kind of wanted to have like a backup method, like a second stab at trying to find contracts doing RLP decoding. And we wanted to try doing it through call data. And so if we're going to look at call data, we need to understand Solidity ABI encoding. So there's a few cases here. You've got fixed size type, dynamic size types, arrays. We don't need to get into any of them too much in detail, except for the dynamic size types, because these roots and these RLP data are going to be passed as bytes objects. So let's see how bytes objects look like in call data. So if I want to encode A, B, C, D, E, F as bytes, the first thing you do for dynamic data is you prepend the length, padded to 32 bytes. So A, B, C, D, E, F, it's 6 hex characters, so that's 3 bytes. So we put 3 at the beginning, and then you just slap on the data at the end. And so if you recall, we are trying to detect RLP data, recursive length prefix data. And we have a length field from the ABI, and RLP has a length field. So is there any way that we can kind of use the synchronicity of these length fields to detect RLP data? And the answer is yes. So if we look at X, that is the first word, that is 217, and then Y is the beginning part of an RLP payload. And so we look at F9, that's, we can decode, we subtract F7 to get 2, so it's a long list. So 2 is what's known as the length field, and that is the 214 in blue, because that's 2 bytes. So we know, so the RLP data is telling us from that point onwards, the length of this payload is 214 bytes. So if we add on the length of the payload, the length of the length field, and the length of the prefix, we have 214 plus 2 plus 1 is equal to 217. So these two lengths match up, and therefore we can say kind of with some certainty that this is in fact RLP data, because the chance of this happening with any 2 words inside the call data at random is extremely low. So using these 2 approaches, we were able to kind of get a data set of contracts and of transactions. We started filtering through them in about a week and a half, and we came up with kind of a list of who we thought was affected. And kind of to summarize what we found that most bridge applications on Ethereum weren't actually affected. And this was because, in fact, the people doing RLP proofs over Ethereum blocks would actually be on other chains as opposed to on Ethereum itself. With regards to Ethereum, there were actually 3 bridges which were affected. That was Layer 0, ZK Bridge, which builds on Layer 0 as far as I'm aware, but feel free to correct me, and Telepathy. We also noticed that EIP 6466, the receipts route change, actually had a larger impact than the transactions route change. We didn't really see many people doing transaction route proofs on Ethereum blocks inside of Ethereum itself. And so that's kind of all I've got time for today. If you scan this QR code, you can get a link to my slides. You'll also get a page with some resources about, there's some stuff on The Verge, there's some stuff on RLP serialization, as well as links to our studies and to the EIPs. I don't know how I'm doing on time. I don't have time for questions.
Yeah, there are time for question for sure. Anyone? If no, I can ask a question.
Okay, go ahead.
So yeah, you said you kind of filtered down to 100-ish contracts after you applying the I forgot which technique.
Data flow analysis.
Okay, so did you guys check what was filtered out? What are those contracts doing? Because they also had the constants, right?
Yes, but you can be comparing to the the constant, but doing something completely different. it may not be dictating the control flow. We did a sampling of them, and we found the sample that were rejected weren't actually doing RLP data.
I'm just curious, like, did you maybe find out some contract that are verified and then found out they're doing something particularly interesting that are similar to RLP but not RLP?
From what I recall, there wasn't anything super interesting in terms of like contracts that were doing something similar. There is kind of this like interesting thing, like if you try to do it just on source code, like searching for RLP in source code, you actually get like lots of false positives, because even though it's in your source code, it doesn't have to be in your compiled binary, which is why we did this entire study from binaries to begin with.
Okay, okay, that makes sense. Any more questions?
All right, well, thank you for having me. Thank you everyone for paying attention. I hope I didn't bore you.